Log on, tune in, find out. Another good idea from Cambridge.
I believe this is Jesse Alama. You're coming to us from Lisbon.
That's right.
And how long will you be here?
I'll be here until mid-April. Quite some time.
So I look forward to hearing about automated human proofs.
Right. I've always been interested since I first learned about these classical problems in artificial intelligence, about the problems of men versus machines or people versus machines. And I would say this is a contribution in this direction, although I'll try to be more specific now. This is joint work with a couple of colleagues in the Netherlands. I'm officially based in Portugal. So I'll be talking about automated theorem proving and interactive theorem proving. What's the issue here? Well, the issue is that we have, on the one hand, automated theorem provers which are able of carrying out deductions for us. And in recent years, we have seen them become quite strong. And on the other hand, we have a tradition of interactive theorem proving, which is generally using, not using state-of-the-art reasoning, but rather allowing us to write our own proofs and so forth. They're usually using a weaker kind of reasoning. The problem now is that we have a corpus of sometimes quite large corpora of proofs that have been constructed by humans using interactive theorem provers on the one hand, and on the other hand we have automated theorem provers which also have their own notion of proof and can do their things. And how can we compare them? That's the problem here. Well, why are we doing this? Well, having lots of proofs of a theorem, I hope you would agree, is a useful thing to have. And in fact, I'm looking at formal proofs here. And in this project that I'm describing, which is ongoing in recent times, and also I'm still working on it here, is comparing human or humanish proofs to those which are simply generated automatically by a machine. The problem is, how are they different? And the problem, well, I'll talk about one characterization of difference, which is comparing sets of premises. So I said that there's a distinction between interactive and automated theorem proving. So let me explain first the interactive side of what I'm doing. So I'm using the Mizar interactive theorem prover. Mizar is based on set theory and first order classical logic. They're really the antithesis of what we saw in the previous presentation. It's completely classical from the beginning, and its foundations are in set theory. It's been around since the 70s, although it picked up steam in the 90s and in the last decade or so. And by now, we have tens of thousands of results proved in Mizar. Last time I counted, there were more than 50,000. This is really quite impressive. We should be quite clear about what these numbers mean. It doesn't mean that we have that there are, say, 50,000 theorems of contemporary mathematics. Usually the notion of theorem here is somewhat small. On the other hand, there are some, among these 50,000, there are a number of highlights. There are quite a number here. The Jordan curve theorem, this is a really famous problem in topology. Completeness theorem for first order logic. There's some topology here, Euler's polyhedron formula, and so forth. Lots of theorems have been formalized from beginning to end based on just the axioms of set theory and first order classical logic. So already I would say this is quite an accomplishment. Essentially the entire contents of an undergraduate curriculum are now available, proved from beginning to end completely formally, and not just undergraduate mathematics, but much more.
So can you say again what is an interactive theorem prover?
Yeah, right, don't define it. Interactive theorem prover, well, I would say this is just a genre of a program which allows us to state some kind of principles that we want to use in a proof, and then it also comes with some kind of language or some kind of notation for expressing proofs. one submits a text or a proof to the system. It will say this is incorrect step, this is a wrong step, this doesn't make sense. Please change the proof and resubmit it to me again, and I will check your conclusions again. Yeah? As opposed to an automated theorem prover, which generally doesn't work like that. An automated theorem prover, in case you don't know what this is a kind of program that essentially works, well, as it says, automatically. We have some list of premises that are available, some target conjecture that we think may or may not be a consequence of the premises. And the question is, push the button and find out whether that is in fact the case. These systems are usually based on the principle of resolution. This is a principle in propositional or classical logic. And they're usually working in a brute force manner. Of course, that's maybe not quite fair. They're really actually somewhat intelligent in some respect. But for our purposes, let's just say that these are more or less brute force applications of a resolution principle. If you have some experience with automated theorem proving, you know that these systems, despite their power, are really quite limited. It's really almost embarrassing how easy it is to give a problem which we know is valid. We know that the conclusion is a consequence of the premises. And in fact, we might even know a very short proof of that. But in fact, there's no system that can find this proof. So these systems are somewhat weak, and it has to be admitted. So now if we want to take something like the contents of the Mizar library, all these theorems and their proofs, the question is, well, can an automated theorem prover really find these? If I look at the set of premises that are used in the Mizar proof and the conclusion, is it possible to get a proof of the same conclusion using an automated theorem prover? And if so, this would probably give us a different proof, right? However, this is bound to fail, and in fact there are many experiments that show that this generally doesn't work. In fact, if one really is pushing the issue, one is able to prove only about 3 or 4% of all the theorems in Mizar using this kind of naive approach. So what we want to do, here's where the artificial intelligence is coming in. We use machine learning methods, and what we do is we try to learn from successful proofs to see what counts as a successful proof. What were the tricks that we used? Yeah. And let me just give you the result that I want to describe. Using this kind of machine learning premise selection, which I will describe more in a moment. And we use the Vampire automated theorem prover, which is developed here in England, in Manchester. We were able to find about 9,000 proofs. So of these 50,000 that are available, we found slightly less than 20% of them. But I have to be quite careful about the experiment, so now I want to describe how we do that. So first of all, we have, as I said, Mizar is based on first-order classical logic and set theory. And it has its own logic, as it were. I mean, it's intended to be first-order logic. However, there are some little extensions that it has to make formalization somewhat nicer than just raw first-order proving. So there's a problem of translation, because the automated theorem prover, these are typically using pure, untyped, unsorted first-order logic, whereas Mizar is using something slightly heavier. So there's really a translation problem here. And it's really quite non-trivial how to do this translation. In fact, this is really quite an interesting blend, I would say, of syntax and semantics, because the problem is that we are trying to account for all the steps or structures of Mizar, which is a rather rich language. Compare that to the extremely basic language of raw first-order logic. And there's a serious issue there of translation. But in fact, it can be done. So how do we do this? Well, we first take the Mizar library, this vast collection of theorems, and then from each item, or each theorem, say, we compute exactly what Mizar thinks is necessary for this theorem. Then what we do is we use premise-select. We do some machine learning on this. So basically, the idea is we have lots of successful examples. You can look at the Mizar library and say, well, this theorem uses exactly these things, and this gives a kind of correspondence that we can give to a machine learning system. And then we use Vampire to try to prove these again. So MML, this Mizar mathematical library, I said it has a lot of theorems. In fact, if you count all the things that are appearing in the library, including the definitions and things like this, you come up with almost 100,000, or actually more than 100,000 items that could be used as a premise in some problem, some theorem-proving problem. So we have to account for quite a lot here. So let me just give you one example. I will come back to this. So suppose that you are interested in proving a statement about complex sequences and real sequences. So suppose here's an extremely simple result, that if we have a complex sequence which is divided up into A and B with its real and imaginary parts, and suppose that the A and the B n sequences are convergent, then how would we prove that the limit of the sum is going to distribute over, so that we get the limit, or the sum of the two limits? How would we prove that? And let's say we don't know how to do this yet, right? So in a machine learning setup, what we do is we say, well, let's look at all the terms and symbols that are appearing in this problem. So here we see equality, we see the limit operator, there's probably something about sequences that we need to know, there's addition, there's I, the imaginary unit, right, and so forth. So there's some kind of a pattern or characteristic that this problem has, yeah? And then we look, well, if we have a problem that has that kind of features, then what kinds of premises were useful for solving problems using those kinds of features? So we just look at the symbols and the terms in the formula, and then we look at previous proofs that are using these symbols, and maybe others as well. And we were using machine learning methods to select the relevant premises. So think of it like we have our own little mathematical Google setup. You punch this in, and then we give you a rank page of all the things that we think are going to be relevant to proving your conjecture. Now in the Google context, of course, what's most important is what's the first one, right? But here usually mathematical problems are not solved by one premise alone. We need to have many premises, right? So that's the setup. How do we do this? Well, there are about 10,000 symbols or terms that are appearing. Well, sorry, there are about 10,000 symbols and quite a lot of terms that are appearing in the library as well. So if you think about this from a machine learning problem, we have 1 million input features and about 10,000 output features. So in other words, I give you a problem and I say it is characterized by these 1 million features, right? It has plus, it has the equality, it has the limit operator, and basically nothing else, right? So, and then the output features, well, would be what are the possible relevant results for this, right? This is a really challenging learning task. We really had to be quite clever in getting our machine to do this kind of task. We just used a naive Bayes setup, nothing too clever because we wanted to do something fast and space efficient for this problem. We have big guns available to us. We are able to use, thankfully, a machine that has resources enough for us. If you wanted to get these predictions, in other words, if you want to pre-compute our Google, it takes about 1 full day of 100% computation to do this. In other words, it takes one day for each theorem to get this list of possible premises that we think are relevant to solving it, right? So the result is our own giant Google for the Mizar library. Of course, Google itself is much bigger, but yeah. So the MML is the Mizar library is growing from the axioms of set theory all the way to advanced mathematics. Well, so we could try to prove each theorem automatically from all previously proved premises. In other words, anything that comes before a theorem logically could be a premise, conceivably, right, for some problem. So, for example, in the limit, the sum of limits example, we could say that a relevant premise for this could be something like addition is commutative, which might be relevant, maybe not. But something that would come prior to this would be, say, the empty set exists, the union of the empty set with another set is itself. This kind of thing is logically prior, right? But if you do that kind of thing, the results are really quite bad. So in other words, each problem would generally have tens of thousands of premises. Even very simple problems would have huge numbers of premises. And an automated theorem prover, even a very clever one, is going to fail on this kind of case almost all the time. And so for us, we took the number 200 as our limit. So in our Google, we give a theorem and we say, give us the top 200 results. 200, it's somewhat arbitrary. We wanted to have something that wasn't too biased, but we didn't want a number that's so big that the automated theorem prover would fail. So for each problem, we gave the theorem prover Vampire 20 seconds. So it has 20 seconds to prove this theorem from 200 premises. Yeah. And surprisingly, in more than 9,000 cases, we were able to find the proof automatically. So it seems to us that almost 20% of the time, mathematicians don't need to think. They can just punch in their formula to our Google, and they'll just get the proof in 20 seconds. Google is faster, but maybe this is a start.
So just to make sure I understand, is 20% or 18% is from
Yeah.
the list of theorems itself?
That's right. There are 50,000 theorems altogether. And the question is, which of these could be reproved from the list of 200 premises that we think are relevant to it?
What I don't understand is that this 200 will include among them itself. Right? Itself is very relevant.
Oh no! When we're constructing the problems, we don't. We only are using logically admissible.
And what about the little lemma that is just before the big theorem?
That would be, well, that's available for the construction, and if it's using the same symbols, then it's likely to be in this list of 200. Yeah, and in fact, you'll see an example of this coming up.
Doesn't that show that the person who has created the bizarre file
Yes.
has chosen the previous results to help him getting to the proof?
Yeah, that's
So it's not surprising that 20%, 18%.
This is not trivial. So, for example, the first question, why isn't the theorem itself counted as a kind of helpful tip for the theorem? Well, that's inadmissible. We're only using what's logically prior. If we really said that, then this would be more like 99% of, yeah. So
where do you stop? That's what my question is. I mean,
yeah. Mm-hmm.
What do you consider admissible? I mean, the theorem itself is not admissible. That's clear.
Yeah,
but
right.
maybe.
Oh, I see. So
The lemma in the textbook
yeah.
should not be admissible either.
Yeah, that's right. So to be clear, there's an exact order. There's a linear order that can be placed on the entire contents of the library. First comes the axioms, and then the results about empty set and this kind of thing. And then very late in the list, or well, in the middle of the list, you'll find this sum of complex limits thing. So given this linear order of logical admissibility, we select 200. Yeah. We don't select 200 from the whole thing, because almost certainly would, as you say, would just select itself, which would be kind of meaningless, right? Right?
But the 200 are chosen based on the thing you want to prove.
Sorry?
These 200 premises are chosen based on the thing you're trying to.
That's right. That's right. Yeah. So there's a machine learning system. Yeah.
In the library, typically, how many premises are used in the proof of something?
Oh, well, just on average, how many are used?
In the actual existing proof.
How did this go?
You just touch the touch. People make them talk.
Sorry. Yeah, right.
Where are we heading with this now?
It looks like it's coming back.
There.
Yeah. Thanks. I lost my train of thought. Can you repeat the question?
So I was asking, in the actual library,
Yeah.
you have a proof how many premises typically will be used.
Usually, this is about 3 or 4 dozen that are used, that are kind of minimally needed to get this to be correct. But there's quite a lot of variation. Okay, so one part of this experiment is to compute these fine-grained dependencies. I'll just be brief about this. The problem is that ITPs like Mizar, usually when you're formalizing a proof, you're not using, your intention is not that you formalize exactly all details in a sense of a raw Fitch-style proof or a raw Gensen-style proof. This is really kind of out of the question for any serious proof. And so usually interactive theorem provers are making available information to you, and they're doing inferences even though you didn't explicitly say them, just to help you get along with your proof. But the problem for our purposes is we need to recover those. So we have to elicit those implicit dependencies, and that takes quite a lot of work. And in fact, I think it takes about 2 weeks. And that's maybe a lower bound. It might be more like 3 of non-stop computation to do this. Now let me try to give you some sense of how these, or what these numbers are about. We were able to solve 9,000 problems, and now if we compare the sets of premises, in other words, what was minimally needed for the Mizar proof and what's minimally needed, or what was in fact used by the automated theorem prover. Yeah, these are 2 sets for the same theorem. There are a number of cases where the sets are equal, which is perhaps maybe a bit surprising, given how many premises were available for each problem. There are a handful of cases where somehow the human proof is better in some sense than the automated theorem prover proof. There are quite a number of cases, which is maybe also not surprising, where the automated theorem prover is able to give something sharper than the Mizar proof. And logically, the fourth case is that the sets are orthogonal. There's something that's in one but not the other. There are all sorts of puzzles here about what it means to compare proofs, given that they are written in 2 totally different styles. Usually there's the resolution style by the automated theorem prover, and on the one hand, and on the other hand, we have the Mizar proof, which is a kind of natural deduction proof. So they can't be literally compared. So we're comparing sets of premises. But now think about a case like this. If we have a set of orthogonal premises, or even one of these 3 cases where they're not equal, is it possible that even though they are apparently equal, that in fact they're really the same proof? So here's one example. So suppose that we have statements A, B, and C, where A logically implies B, let's say from no premises except A. B logically implies C, and suppose we have a proof of C from A and a proof of C from B, yeah? Well, are these 2 proofs really different? Well, maybe not, right? It's not clear. In some sense, if we expand the premise B, then we recover A, right? Yeah, and then from this perspective, we might say that they are the same proof. Yeah, or to be more precise, they're using the same, let's say, mathematical or non-logical information. And often when there's a disagreement between the sets of premises that are used, we can recover that by expanding premises in this way. Let me talk about briefly the case where the Mizar proof, or I would say the human formalized proof, is somehow using a sharper set of premises than the theorem prover. So in this case, the Mizar proof is somehow, at least on the surface, a generalization, or more general than the ATP proof. Although when we investigate, we see an interesting phenomenon here. So it turns out that the theorem prover, usually this is just reporting the very first proof that it finds. There might be lots of other ones, but usually the goal is simply to find a proof, and it will stop if it finds one. It doesn't check whether all the premises that it actually employed somehow doing the proof are actually necessary. So which premises are junk? Well, let's say that a junk premise is a one that has the same class of models. In other words, we have a theory and a theory minus some formula, but these have the exact same class of models. Well, can we always remove the junk? The answer is no, not practically, because it turns out that sometimes if you give the theorem prover fewer premises, even if you know that these fewer premises are still sufficient, it may simply fail. But if it will succeed if these extra junk premises are present. So in some sense, although these automated theorem provers, of course they are intended to be complete, in some sense they might be practically incomplete. It might be practically necessary to have some junk premises, and that's what we see this time. I'll skip these other characterizations. I'll be around for months, so you are happy to, or I'm happy to talk about this at any time. Let me mention one case that was just briefly suggested here. So suppose that we have this theorem about negative numbers. If A and B are real numbers, A is less than or equal to B and B is negative, and so is A. Yeah, that seems clear. And there's a proof of this, and it's using the transitivity of the less than or equal to relation. It's really quite obvious, right? Here's something that occurs slightly later. If A is less than or equal to B and A is positive, then so is B, right? If you look at the proof of this, in fact, it appears to be obtained by copy, paste, and edit of that proof. Yeah? But in fact, the theorem prover noticed this earlier result and just simply immediately proves this. Using classical logic, if you were to write this out in, say, a clausal form and this in clausal form, we could recover it very quickly. But in fact, the human proof is somehow a duplication of this previous one, right? So what's going on here? It seems that the human formalizer, I don't know, I mean, didn't know about the previous result, or didn't care, or so forth. The proof is longer, whereas the vampire proof is much shorter. Let me wrap up by talking about, well, I'll just wrap up here. So we found, maybe this is not too surprising, that when it does succeed, the theorem prover will find simpler proofs. It doesn't always succeed. In fact, it's failing on 72% of cases. 82% of cases. But when it does succeed, it's usually using somewhat slightly clever tricks. So if you're interested in maintaining these kinds of things, for example, if you're interested in finding these copy, paste, and edit proofs, by the way, think about this. How many proofs in the library there are copy, paste, edit from some original source, right? This is an interesting puzzle. So these results suggest a number of problems about the mapping of these interactive logics into say, non-interactive logic, like pure one-sorted, first-order logic. And there's an interesting blend here of syntax and semantics. If you want to ask me about that, I'd be happy to talk about it. If you're interested in theory, I would say that these kinds of results are at least the beginnings of a resource for proof mining and proof analysis, or even theoretical criteria of proof identity. I would say, because we have really two different kinds of proofs and two different sources of proof. I think that if we were to find large differences, this might even help give us a sense of interesting cognitive differences between, say, a human and a machine. So for example, it turns out that we've seen that in human proofs there's a preference for somehow going back to definitions and expanding definitions as a way of solving the proof problem, whereas an automated theorem proofer can just use previously proved facts and somehow doesn't have to go back to definitions and re-expand them. Lots of notions of proof comparison and proof metrics are available. We have so far a very coarse one, just looking at the set of used premises. And we even have a kind of line count metric, but this is really under development. Thanks for your time.
Any questions? I guess the natural question I was thinking on, you're sampling theorems already in your collection. So if you just open up a random undergraduate textbook and put out a theorem, is it already in your database, or will it be proved?
It's yeah. So you really pull out something from undergraduate mathematics. The chances are that well, so you're asking me what are the chances?
Exactly, because you've been experimented with.
So I'm trying to maybe promote this a little bit, but it's true that there can sometimes be embarrassing little gaps. I mean, so for example, if nobody proved exactly the CELO theorems, then, but they proved something that's kind of just before it, then you have to say there's a gap there, right? But,
on a lighter note, I see that you are also a fan of Futurama. Can you testify as to whether Bender or Fry has ever proved a theorem?
I would say that the answer is no. Yeah.
Thanks.
Thank you.